Okay. So, what are the chapters in the book? Froment and Bischoff second chapter, and Davis and Davis primarily chapter number 5. Chapter number 7 is what is called as microkinetic modeling. So, if you have the original detailed model containing tens of reactions, how can you simulate those models, how can you analyze the overall system? That is what chapter 7 talks about. Chapter 5 talks about how to derive a reduced rate expression or a simplified rate expression from detailed rate expressions. Okay. So, there are several examples of solid catalyzed reactions. It is one of the most common type of reactions in the chemical industry, especially the petrochemical industry. Some of the examples are isomerization of N-butane to I-butene, acid or base catalyzed dehydration of alcohols. You have CO oxidation, for example, CO oxidation will be promoted on say palladium based catalyst or platinum based catalyst. Reduction of NO and simultaneous oxidation of CO. This is used in automotive exhaust emission catalysts in order to remove both carbon monoxide and NOx. In all your petrol engines, you have this catalytic converter. That catalytic converter basically consists of platinum, rhodium and palladium based catalysts, and that is something that is used very commonly throughout. It is one of the most common examples of solid catalyzed gas phase reactions. Water gas shift, steam reforming, ammonia synthesis, all of the examples, a large number of examples that we have taken so far in this course are of solid catalyzed reactions. There is also a reason for that. My research is in solid catalyzed reactions, and that is the reason why a lot of examples that we have taken are of solid catalyzed reactions. Okay. If you look at chapter 2 of Froment and Bischoff, okay, they talk about various different reactions, whether that is one reactant or two reactant or one product or two product. Okay. So, one reactant, two products, one reactant, one product, two reactants, one product, one reactant, two products, two reactants, two products, and these are taken as examples, prototypical examples of a large number of cases. And as you can see, these covers probably around 70-75% of the cases that you are going to encounter. Okay. This is one reactant, one product, this is one reactant, two products, two reactant, one product, two reactant, two products. Okay. So, a large number of cases, probably 2/3 of the cases are covered by these examples, and that is the reason why they have this particular mechanism. So, you can go and read your Froment and Bischoff, and you can see the derivations or the generalized derivations for these cases. If you see your assignment, let us look at your assignment 2. Okay, the last couple of pages of your assignment, this is not for you to submit, this is just for information. You can derive various laws for all those 4 type of reactions, and they fall in some particular manner, okay, and that is summarized in Froment and Bischoff in these couple of tables, table 2.3.1 and table 2.3.2 and table 2.3.3. So, those tables are where these are, or sorry, 2.3.1-1-2-3. Those are the 3 tables in which in Froment and Bischoff these are summarized, okay, and how you can make sense of this, what typical patterns do emerge, how you can look at the rate of reaction and try to postulate what might be the mechanism, all of that we are going to cover over the next 3 lectures and 1 tutorial. Okay. So, that is our game plan. So, although and over so many years I have gotten feedback, a feedback that I agree with. We keep doing every time A plus B, A plus C, A plus B going to P plus Q, A going to P, A going to Q. Can we take examples? So, yes, what we are going to do in this part of the course is take some examples as well as stick to A, B, C. Okay. So, we will try to do both. ABC is so that you realize that the concepts are more general, things like ammonia and water gas shift and so on, is to ensure that we do not miss why we are doing all of this. We are doing all of this because it has practical significance. Okay. Okay. So, when we talk about catalytic reactors, okay, the most common type of catalytic reactors, if you look at some of these examples. So, in examples like these two, you will have this reaction taking place in what is called as catalytic monolith reactors. What are monolith reactors? Is basically it is a large block of ceramic, okay, and in this large block of ceramic you have multiple holes that are made. Okay. How many holes are there? The number of holes that are there is as many as 400 channels per square inch. Okay. Sometimes there might be up to 900 channels per square inch. Okay. So, literally the monolith is this large, and this large monolith will have something like 1000 channels going through. Okay. How do those channels look like? Each channel is going to look like a tube. Okay. The tube diameter is of the order of 1 mm. Okay. It is 700 microns to 1 mm. So, that is 0.7 to 1 mm is the diameter. Okay. The catalyst is coated on the inner walls. Okay. So, this blue color represents the catalyst. Okay. So, as the reactants are flowing, they will diffuse to the surface. As the reactants are flowing, they will diffuse to the surface and the reaction will take place on the surface. Okay. That is one example. The other example is something that you have encountered multiple times before. These will often be carried out in packed bed reactors. Okay. So, these will be pellets of size say 1 millimeter, 2 millimeters, 5 millimeters, 1 centimeter and so on. So, small size pellets, okay, and the entire reactor will be packed with those pellets, including some things to ensure that there is no flow channeling, flow is well distributed and all that, including structural things to ensure that under the weight of the catalyst, the lower pellets of the catalyst don't get crushed. Okay. If for example, this fixed bed reactor is say 2 stories tall, then the bottommost pellets will have a lot of weight coming from the top and they can get crushed. So, there will be a lot of structural elements to ensure that that does not happen. Okay. So, that is what a fixed bed reactor consists of, but as far as we are concerned, there is going to be catalyst pellets that are present within the reactor, and those pellets are where the catalyst is present. Okay. So, based on that, we will take a slice of that reactor. Now, this small slice that you see over here could be a slice of the wall when it comes to the tubular reactor, or it could be a pellet. Okay. So, if it is a wall, okay, what we have is basically your catalyst that is present over here, or if it is a pellet, okay, it is going to be a pellet like this. Now, whether it is a wash coat on the wall or whether it is a pellet, okay, most often these are highly porous. Okay. What do you mean by highly porous? If you look at the surface, okay, the surface is not going to be smooth like this, but instead it is going to have multiple pores. Okay. Within these pores, there will be active catalyst that is present. Okay. One of the common techniques for getting the active materials on to the catalytic pellets or the catalyst wash coat is what is called as incipient wetness method. So, if you are in catalysis program or if you are interested in catalysis, there will be a lab that will be running next semester. So, that is on catalyst preparation and characterization. So, if you are interested, you can take that lab for as a part of your MTech program. If you are a CH MTech, if you are a CA MTech, then it is a required lab. Okay. So, what is done is basically you will take that pellet, you will dip it in basically a solvent containing small amount of the salt. So, salt would be, for example, platinum salt, palladium salt. Okay. How much water will be? So, this would be basically platinum, palladium and rhodium, a mixture of platinum, palladium and rhodium dissolved in water. How much water will you use? Just the amount of water that will go into all of the pores of the catalyst. So, you take that catalyst, you put water so that it goes into the pore. Because the catalyst is porous, you keep it soaked for some amount of time. After some amount of time, all the water would have gone inside the pore. So, think of it like a sponge. Okay. So, how much water you are putting? You are putting just the right amount of water that the sponge gets soaked, not so much water that the sponge starts overflowing. Okay. Then what you do is you dry it, maybe overnight or maybe for 24 hours you dry it. Water goes away, the salts stay. Okay. Then you dry it at certain higher temperatures, let us say 80 degrees Celsius and so on, so that all of that water goes away. Thereafter, you take that catalyst and you do a calcination process. What does calcination do? Basically, these are all salts of metals. So, for example, platinum nitrate or acetonate or whatever else salts might be required, or chlorides and so on. Okay. So, you heat it at a very high temperature so that all of these ions go away, and what you are left with is platinum, palladium and rhodium on the catalyst support. Okay. Once that is done, you now have active catalyst. How would that catalyst look like? That catalyst would look as I have shown over here. Okay. Because you have taken just the amount of liquid that will go inside that sponge. Okay. Most of the catalyst will be deposited inside the pores. Okay. Some amount might be deposited on the surface. There might be some amount deposited on the surface, but mostly it is going to be inside the pores. Okay. That is how the active material will be deposited. Okay. Now, think about it. So, this is how your catalyst is. Okay. And this is how your reactants are flowing. Okay. So, what are the various processes that are happening? Okay. One is the advection or convection, that is because of the bulk flow. Okay. Second is diffusion. So, if you have flow going in, there will be diffusion towards the periphery. Okay. Then it comes across the catalyst. Once it comes across the catalyst, there will be diffusion within the pore. Once it diffuses within the pore, it will go to the catalyst active site. Okay. And there will be reaction that is taking place and the products are going to be formed. These products will diffuse back outside the pore and then it will come back into the bulk and flow. Okay. So, this is what this particular image shows. Okay. So, what is happening? You have bulk flow taking place, you have external diffusion taking place, this is module 5A, you have internal diffusion taking place, this is module 5B, you have reaction taking place, this is module 4, you have diffusion back into the system, okay, and you have the net flow and the overall behavior of the reactor, and that is module 8 and 9. Okay. So, that is how we are going to tackle this. Okay. So, in this particular module, we are going to look at processes that are happening on the surface. Again, external diffusion, that is diffusion from the bulk to the surface of the catalyst pellet. Internal diffusion from the surface of the catalyst pellet within the pores to the actual catalyst site. Reaction, which involves adsorption, surface reaction, desorption steps, that is what is happening on the pellet, that is the mechanism that is happening. We are trying to derive rate laws from mechanisms. That is what we are going to do in this particular module. Okay. Okay. So, some notations, we will use CAB to say concentration of species A in the bulk fluid. Okay. So, at this location we have CAB. Okay. CAS is concentration on the surface. Okay. CA, we will use CA, so CA is something that varies. In the bulk, CA takes the value of CAB, on the surface CA takes the value of CAS, within the pore CA varies from the surface right to the center of the pore. Okay. So, CA is a variable that varies along the catalyst coordinate. Okay. Now, the CA, the species A has reached the catalyst. Okay. Once it has reached the catalyst, it will adsorb. Okay. The adsorption reaction we will represent this as A plus star giving A star. Usually, for the most cases, we will say the adsorption is reversible. Okay. What does that mean? That means that A is present in the gas phase, whether it is the bulk or the pore. Okay. It comes and sits on the surface. Okay. Why does it sit on the surface? It sits on the surface because adsorption is an exothermic process. Okay. It could be physisorption, it will be, if it is physisorption, it is exothermic process with energy equivalent to say 10 to 20 kilojoules per mole, okay, approximately 4 kcal. Okay. Or it could be chemisorption, in which case the energy of binding, the binding energy of that species is higher, it is maybe 4 times higher than that. Okay. So, that is what happens. A few other terminology will define coverage on the active site. Okay. Coverage is basically a fraction, okay, concentration of A divided by the concentration of all the active sites. Okay. So, let us look at this particular example. Okay. There are 6 active sites. Okay. What is going to be the concentration of A? Let us say concentration of A is 2. What is the coverage of A? 2 by 6. Okay. So, concentration of A is 2, the total concentration of all the active sites is 6. So, theta A is 2 by 6 or 1 by 3. What is CB star? 1. So, what is theta b star? 1 by 6. Okay. In all of these cases, we are going to assume monolayer. Okay. Therefore, our thetas are going to necessarily take a value between 0 and 1. Okay. There cannot be negative values, there cannot be values greater than 1. Okay. There is one more thing which we are not going to consider. Some of the species might adsorb not on one site but on two sites. Okay. So, for example, your ammonia might adsorb like this, or usually for example CO2 might adsorb like this. Okay. In which case, what is the concentration of CO2 here? If only one molecule is adsorbed, CO2 concentration is 1. Okay. Your gamma is 6, but what's your theta? 2 by 6. Okay. So, just to tell you that what we are teaching in this class is not the entire picture, there is something beyond this. This is the case, dual site adsorption is something we are not going to cover in this class. Okay. Just if you encounter in your research, I am just letting you know that there is more to it than only the things that we are teaching over here in the class. Okay. As far as we are concerned, we are going to consider cases in which a particular atom or a molecule will be adsorbed on, when it is adsorbed it will only occupy one active site. Okay. But that does not cover all of the cases, just to let you know. Yeah. CAS typical units is in moles per centimeter square or moles per meter square. So, same as gamma. Okay. Oh, CAS depends on the situation, but typically it is moles per centimeter cube. All of these three. Okay. It is not monolayer. It does not mean anything in the context of reaction mechanisms. Okay. If you have multi-layer adsorption, there are different ways to tackle it. The way that we will tackle multi-layer adsorption is by defining additional quantities to take care of the multi-layer adsorption. If we are talking about multi-layer adsorption in reacting systems, if we are talking about multi-layer adsorption to probe how adsorption happens, okay, there are examples of multi-layer adsorption. So, BET is an example of multi-layer adsorption. What BET talks about, and again because you asked a question, I'll just quickly answer that. So, you have for example a surface, you have one layer of molecule that comes and adsorbs on that surface. Okay. After that is complete, the next layer of molecules will come and adsorb, and more layer and more layer and more layer, and the idea over there is that the energy of interaction between the various layers is the same. Okay, so there are certain assumptions that go into various different types of adsorption models. Okay, the Dubinin-Radishev or the Dubinin-Estakov models are models that are used for microporous materials. Microporous materials are materials where the pores are submicron size. Okay, so when the pores are that, there is an effect called pore filling effect that happens. Okay, sometimes what you get is an effect called pore condensation. So if there is pore condensation, if it is pore filling, it's a DR model. If it's pore filling with condensation, it's a DA model. There are some differences in that. What we have talked about is Langmuir adsorption. There's something called multi-site Langmuir. There's another adsorption called Unilan, which is basically Langmuir adsorption. So Langmuir adsorption will be that A adsorbing on a surface will have one particular value of delta H. Unilan is the value of delta H, heat of adsorption, will lie between say 3 kcal to 4 kcal as a probability distribution function. Unilan assumes that the probability distribution is flat. Langmuir assumes probability distribution is a delta function, a Dirac delta function. Remember process control, Dirac delta? Yeah. So that's what Langmuir adsorption assumes. So there are different types of adsorptions. Which one to use for a lot of materials it is known, but for a lot of modern material there isn't a consensus that this is a right one or that is the right one. In fact, in sometimes what we do is we extract the data from the equipment and then we try to use computational catalysis tools such as DFT and so on in order to extract the information about what is actually happening. Okay. So, all of the tools that we are talking about are introducing you to the overall subject. There is a lot more variety, especially in the last 20 years when we are able to probe what is happening at the molecular level and at atomic level, and now even subatomic level. We are able to probe these systems and we are finding more and more things that we can do with these materials. So that's the reason why you have all of this. So to answer your specific question, if we are talking about multi-layer adsorption with respect to physisorption, with respect to capture of gases or pollutants, that's a different subject, and you will have to use appropriate models for that purpose. If we are talking about reacting systems, okay, if you are talking about say third layer or fourth layer of adsorption, there is not enough interaction that is present over there to really call it catalytic. So we don't address it in this type of formulation. Okay, slightly longer answer, but that's okay. Just want to give you a complete picture. Okay, so let's talk about catalyst mechanisms. The simplest mechanism that again in your undergraduate you might have studied is A plus star giving A star okay. This is adsorption, this is surface reaction, this is desorption. Okay. Most of these reactions and especially the adsorption desorption reactions are reversible. Okay. We often say that a particular reaction is irreversible, rate limiting step and so on. Those assumptions will be given to you. Okay. How we can get from various things, various tools, we will talk about it after the tutorial for this module is done. Okay. But we are not going to limit ourselves to this. Okay. Our attack is we are going to first talk about adsorption desorption steps only. Okay. That is what I am going to do in the next 10 minutes. Okay. Thereafter, the surface reactions we will bring in the next class, and we will use all of these to talk about how you can get the overall rate of reaction. Okay. So with this we started this course with ammonia synthesis. Okay. In ammonia synthesis, these are adsorption desorption steps and these are surface reaction steps. Okay. Keep in mind the desorption step is just reverse of adsorption step. Okay. So, for desorption I will say K dash is the equilibrium constant and K I will talk of as equilibrium constant for adsorption. Okay, that is the terminology that we are going to use. Okay. So, we will use the terminology K1 in this particular example. Okay, we'll come to that in the next lecture again. Okay. So, the tools that we are going to use is pseudo steady state and partial equilibrium. The other tools that we are also going to use is most abundant reactive intermediate and rate limiting steps. Okay. What do these mean? How we are going to use is what this module is about. Pseudo steady state, if species X star is in pseudo steady state, this implies okay, exactly what we have done in module 3, no difference. Okay. So, let us take this example. Okay. The rate constants are K1 and the system is in partial equilibrium. Write it down, next 5 minutes is on you. What is rate of forward? Backward? Okay. Typical rule of thumb, express theta x star as much as possible in terms of theta star. Okay. Let us say you have 5 species, theta A star, B star, C star, D star, E star and then star. You need 5 equations to eliminate A, B, C, D, E. 6th equation is going to be side balance. Okay. So, what is theta NH3 star? Okay. It is K1 divided by K minus 1 multiplied by okay. This is nothing but capital K1. If it is adsorption step, we will write this as KNH3. If it is desorption step, it is K dash NH3, which is nothing but 1 divided by KNH3. You remember? We have done this, right? As state function. Likewise, delta G is state function. So, A to B or B to A. So, K of A to B multiplied by K of B to A equal to 1. or K of A to B is nothing but 1 divided by K of B to A, okay. That is how it works, okay. What will be the side balance? Yes, theta star plus theta NHC star equal to what? 1, okay. All the species that we are considering, when we sum it up, that they end up being equal to 1, okay. So, then we substitute this over here and what we will get? Theta star 1 plus okay. So, theta star is 1 divided by 1 plus okay, or this Langmuir adsorption. Okay. If we were to plot theta x versus px at very low values of p, 1 is much greater than kp, so you will get linear. At very large values of p, you will have k1 p nh3, k1 p nh3 cancel off, so it will level off at theta equal to 1. It will smoothly go from 1 to from slope of 1 to a value equal to 1. So, this curve is going to look like this. So, with that we will end this class today. Okay. What we have done is done a few definitions, looked at generic reactions. We talked about how the concepts we are using in module 3 will be used in this particular module. We took up an example of adsorption of single species. What we are going to do in next class is look at another adsorption. This is of hydrogen, which is called a dissociative adsorption. We will see how this differs from adsorption that we looked at in today's class. Thereafter, what if both the species are possibly adsorbed? What if there are all 3 species adsorbed? Okay. So, by midpoint of the next class, we will complete various cases of adsorption, and then we will look at the ammonia reaction and how do you obtain an LHW model for ammonia reaction. Okay. So, that is our game plan for the next lecture. Okay. Alright. Any questions? Okay. Not, thank you very much, and we will see you in the next lecture.